Welcome to the video lecture on sections 4.4 and 4.5. This lecture covers contingency tables and conditional probabilities. Before we begin the lecture, you'll want to have your printed notes available, and they should look something like this. You can download them from the course webpage under the Chapter 4 folder. Now, the topics of contingency tables and conditional probabilities are actually quite helpful. These topics will provide you with some tools for summarizing and analyzing data. And these techniques and vocabulary are particularly useful in practical field research. A conditional probability is the probability that an event B occurs given that we know that an event A also occurs. It's called a conditional probability, and the symbol for it is the usual probability symbol, then the event B, a vertical bar, and the event A. It is read the probability of B given A. We call A the given event. Conditional probabilities can be computed with this formula. The probability of B given A is the probability of B and A divided by the probability of A. Now, if we're fortunate enough to be working in an equally likely sample space, and only then, we can compute conditional probabilities by counting outcomes. In that case, we would say that the probability of B given A is the number of outcomes in B and A divided by the number of outcomes in A. Let me just remind you that B and A means intersection of two sets in the mathematical sense. Let's compute some conditional probabilities just to make sure that we understand these basic ideas. If we're going to be computing some probabilities for a standard 52-card deck, we have four different suits: spades, hearts, clubs, and diamonds. The spades and the clubs are black, hearts and the diamonds are red. What we'd like to compute in this case are these probabilities. What is the probability that a card is a club given that it is black? Practically speaking, that means we'd start our deck out first between the red and the black cards, and then we'd draw a card at random and check to see whether it is a club. The probability of a club given that the card is black is the probability that a card is both a club and black divided by the probability that it's black. In this case, that would be 13 divided by 52 divided by 26 divided by 52, because there are 13 cards in the deck that are both black and clubs. In fact, all clubs are black, and there are 26 cards out of the 52 that are black. Notice we could simplify it in this case to saying simply 13 divided by 26, so we'd be cutting back here to simply counting the cards, since the cards are equally likely to be chosen. If we were to reduce that fraction, we'd see that the probability is 1/2, or then 50%. What we want to notice right away is that the order that we list these events is important. The probability of a club given that a card is black is not the same as the probability that a card is black given that it is a club. The probability that a card is black given that it is a club is the probability that a randomly selected card is both black and a club divided by the probability that it is a club. The number of cards that are black and clubs are 13 in the 52-card deck, and the number of cards that are clubs, again, are 13 out of the 52 cards in the deck. So the probability that a card is black given that it is a club is 1 or 100%. Of course, in this case, we didn't really need the help of mathematics to tell us that. If we've chosen a club, it's automatically black. So then the probability that we've chosen a black card given that it's a club is automatically 100%. Finally, let's compute the probability that we've chosen a jack if we know that we've chosen a face card. Now, the face cards are these. They are the king, the queen, and the jack of each suit. The probability of drawing a jack given that we've drawn a face card is therefore the probability of a jack and a face card divided by the probability of a face card. Of course, since all the cards are equally likely to be chosen, we can work with counts rather than probabilities. Now, how many jacks are there in the deck of cards? There are 4 jacks, 1 for each suit. And how many face cards are there? Well, there are 3 for each of the 4 suits. And therefore, the probability that we have drawn a jack, if we know that we've drawn a face card, is 1/3. We sometimes compute conditional probabilities by reading from contingency tables. These are also known as two-way tables. These tables can contain either frequencies, that is counts, or they can have probabilities directly. Here are 2 examples. Tabulated the counts of professors on a faculty according to their age and to their academic rank. It's also possible to list these entries as probabilities, and we've done that in this version of the table. When we work with a table such as this, the entries in the interior of the table, in this region here, are known as the frequencies. Around the outside, we have row totals, column totals, and a grand total. These are known as the marginal distributions. Let's use this table to compute some probabilities. First of all, let's make sure that we know how to read the entries that are in the table. The first question we have here is n of R2 and A3. First of all, the n means we're supposed to report a count or a frequency that's in a table rather than compute a probability. R2 refers to this second column of the interior of the table. It corresponds to the second academic rank of associate professor. Then we're also supposed to find those entries that are not only of rank 2 but of age group 3. Age group 3 is here in this row, so to be in rank 2 in age group 3 means that we're looking at this entry and there are 125 in that category. Likewise, we're asked to compute the number at rank 3 and at age 4. Rank 3 and age 4 is this entry in the table, 36. The next question concerns a probability. What is the probability that a randomly selected member of the faculty will be in rank 3 and age 3? Age 3 and rank 3 is this cell here, so there are a total of 61 individuals in that category. There are a total of 1,164 on the faculty altogether, and therefore the probability is approximately 5.2%. Let's look now at some of the conditional probabilities, and I'll leave the rest to you as practice. What's the probability that a randomly selected professor is of rank 1 given that he or she is in age group 3? Well, that means we need to compute the number that are in rank 1 and age group 3 divided by the number that are in age group 3. The number that are in rank 1 and age group 3 are here, 156. The total number in age group 3 is found from the marginal distribution, 348. This number is approximately 44.8%. Finally, let's compute the probability that a randomly selected member of the faculty is in age group 3 given that he or she is in rank 1. The denominator once again comes from the second event, which in this case is rank 1. In rank 1 there are 430 individuals. For age group 3 in rank 1, we find 156 individuals. that gives us a probability of approximately 36.3% of choosing someone in age 3 if we choose exclusively from academic rank 1.